Next topic in circular motion is the law of universal gravitation. The equation looks awfully intimidating, but don't get all worried up about it. The law of universal gravitation explains the force of gravity between objects. The only reason that we experience gravity on Earth is because we're standing on the Earth. For all intents and purposes, mass causes gravity. And there may be some particles that are responsible for it in the end, but as far as we're concerned, if an object has mass, it has its own gravitational attraction. So everybody in this room has their own small gravitational field. So everybody in this room is attracted to everybody else in this room. And the bigger you are, the more attraction that you have. You are also attracted to the tables and the walls and the pencil in your hand. Everything that has mass has its own gravity. Now, why do we feel the gravity of the Earth as opposed to the gravity of the person sitting next to you? It's much, much more massive. Mass has a great deal of effect on the force of gravity. It takes something the size of the Earth to have a significant effect on somebody's lives. Our moon has its own gravity. It's about 1/6 that of the Earth. So if you were on the moon, you could jump 6 times higher. You would experience 1/6 the amount of normal force, and therefore 1/6 the amount of friction, and other various things. Mass causes gravity. Also, the distance that you are from the object affects gravity. So the further you get away, the less gravity is. Now, I don't know if it's effix or affix. Affects? Is it A? It's affix? Whatever. It's physics, so it affects gravity inversely. And not only inversely, but inversely squared. So the further you get away, if you double your distance, the force of gravity actually goes down by a factor of 4, double squared. If you multiply your distance by 10, gravity will go down by a factor of 100. So it's an inverse square relationship between distance and the force of gravity. So when you're in space, you're not actually gravity-free. The gravity has reduced itself significantly, but if you were stationary in space, you would actually still feel the effects of gravity. So why do people appear weightless when they're in space? Well, Newton had a thought experiment that dealt with this. Here's the Earth, and there's a mountain on top of the Earth. And you go up on the mountain and you shoot a cannonball. If you shoot that cannonball, it goes and it lands on the surface of the Earth. What if you shot it a little bit harder? It would go and it would land on the surface of the Earth. And if you shot it even harder, it would go and land on the surface of the Earth. What if you shot it so fast that the amount of distance that it fell was actually the same amount as the Earth curves? So it falls a little bit, but the Earth curves a little bit. It falls a little bit, the Earth curves a little bit. It falls, Earth curves, it falls, the Earth curves, it falls, and falls, and falls, and falls. So it's in constant free fall, but it never hits the Earth. It comes back and hits you in the back of the head. This constant free fall is what we call orbit. So when an astronaut is in orbit, he's actually falling all the time. So he appears weightless, because when you're free falling, you don't have any weight. There's no normal force to hold you up. So when you see those people floating around in space, they're just falling, and they're falling really, really fast, but they're not hitting anything. So it's a free fall. Gravity out here still exists, and it's a pretty high value, maybe 5 or 6 meters per second squared. So you're not really that far away from the Earth. But since you're in orbit, you appear weightless. So Law of universal gravitation is F sub g, stand for the force of gravity, capital G, m1, m2 over r squared. So the force of gravity at any location, this is a universal law, so it works on the moon, it works in the middle of space, it works near the sun, it works everywhere. The force of gravity equals G, and G is a constant, 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. A really, really annoying constant. That constant was discovered through experimentation. A guy named Cavendish set up a gravitation question, or gravitational. Basically, he took two really massive balls, two really small balls, and then they were gravitationally attracted to each other. Through that experimentation, he discovered the unit of G. Mass 1 is one mass in kilograms, mass 2 is the other mass in kilograms, and then r is the distance that you are from the center. R is the distance from the center of mass. Not from the surface of the Earth, not from the surface of the moon, but from the center of the moon, or the center of Earth. It's really, really important that you make it the center, because it changes your numbers dramatically. Suppose I wanted to figure out what the force of gravity on this pen was. Drop the pen, and it accelerates, right? So here's a free body diagram of the pen. mg. Suppose I didn't know what g was. I'm on a weird planet that looks a lot like the Earth. Has the same radius and the same mass as the Earth does. So I take a pen and I drop it, and I want to figure out what's gravity on this weird Earth-like planet. I solve it the exact same way as I do my other problems. I have a free body diagram. I apply F equals ma. The one force that's acting on me is the force of gravity. That equals to the mass times that mass's acceleration. Well, since I don't know what g is on my planet, I'll use the law of universal gravitation. G, m1, m2 over r squared equals the mass times the acceleration. Here's my planet. Here's my pen. m1, m2. Mass of the object doesn't make any difference. If I dropped an elephant, if I dropped a pen, they would still accelerate at the same rate. Let's discuss that when we did projectile motion. Good thing. So the acceleration depends on this constant, the mass of my object, so in this case it's the mass of my Earth-like planet, divided by the radius. Measured from the center, it's the radius of my Earth-like planet squared. Matthew, can you grab a textbook, a second shelf, right in the middle of those, the other ones right next to it? And in the front cover of that, I think it's the front cover, maybe the back cover, on the inside front cover rather, inside front cover. It should have constants. Does it have the mass of the Earth and the radius of the Earth? You might check the back cover if it doesn't. What's the radius of the Earth? Ten to the what? 6 kilometers or meters? Meters. Okay. And we're going to square that value. and multiply it by 6.67 times the negative 11th with all the units on there. And what is that number? I would take the time to practice typing this into your calculator. Those of you who took chemistry last year, which I think is everybody, will be better at this, but you can still screw this up pretty badly in a calculator. Gravity. With an Earth-like planet, the same mass and same radius, the acceleration you'd expect is 10 meters per second squared, which it is. So you can actually calculate local gravity using that little equation there. You could calculate the gravity on Earth, or the gravity of the moon, or the gravity of the sun. All you need to know is what the mass of the object is and how far you are away from it. So let's calculate gravity of a person. Connor is exerting some gravity on Lindy. Right? How much gravity? Well, 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. Mass of Connor in kilograms? 40 kilograms? We'll call him 70 kilograms. 150 pounds, 160 pounds? Way more than that? 90 kilograms then. Doesn't really matter. 90 kilograms. And how far are you guys apart? 2 meters? So what gravitational attraction does Lindy have to Connor here? 6.67 e negative 11 times 90 and divided by 4. 1.5 times 10 to the negative 9th meters per second squared. Almost nothing. And that almost nothing is counteracted by all kinds of friction. Even air resistance is going to be enough to stop that. How long would they have to wait until they met each other for their long embrace or whatever? Well, it's kinematics. They're 2 meters apart, but they meet in the middle, so there's 1 meter between them. Initial velocity is nothing. 1.5 times 10 to the negative 9 meters per second squared acceleration. T squared. Real quick. That's 1 times 0.5 divided by 1.5 e negative 9. Square root of that value. Time is 1.8257 seconds. Divided by 60 to minutes, divided by 60 to hours. Only 5 hours. So they're 2 meters apart and they're in space. So they're away from everything else. Like even not like close to Earth in space, but outside of our solar system in space. And they're sitting there 2 meters apart. They would have to wait 5 hours before they actually got together. It's a long time to wait. That's not entirely accurate. Technically, when they got closer, the gravity would be increased. So it would be a little less, they would speed up a little bit. But that's not a core problem for us.